In this next section, we're going to take a look at rational exponents. A rational exponent is simply a power with a fraction written where the exponent is. So an example of this would be x to the m over n. If we want to change this to radical form, what we're going to do is we're going to take the n, we're going to move it to the index, and the m is going to remain attached to the base. You don't want to leave a solution as a rational exponent. You always want to take it and change it back into a radical. So in this first problem, we're going to look at what is the simplified form of each expression. And we're given 216 to the 1/3. So 216 to the 1/3, we're going to rewrite that as a radical. So we're going to take the 3 and we're going to move it to the index, and that gives us the cubed root of 216. So hopefully this is one you have memorized, and the cubed root of 216 is going to be 6. So in 1b, we're given 7 to the 1/2 times 7 to the 1/2. So what we want to do is go ahead and change both of those to radical form. So bring the 2 into the nook of the radical, which gives us a square root of 7 times the square root of 7. Multiply those together, square root of 49, which is equal to 7. For 1c, 5 to the 1/4 times 125 to the 1/4. So again, in each case, we've got a 4th root, so the 4th root of 5 times the 4th root of 125. 5 times 125 is 625, and that gives us the 4th root of 625 is 5. Now, if we want to go in the opposite direction, all we're going to do is we're going to take whatever the index is and put it up underneath the exponent. So in this example, we've got the cubed root of x to the 7th, so that is just going to become x to the 7/3. So again, divide the exponent by the index. Again, think of a fraction. We've been doing this over a couple of sections. And then the quotient is the value of the exponent taken out of the radical sign, and the remainder is the value of the exponent that remains in the radicand with the base. So in problem number 2a, what is x to the 3/7 in radical form? Take that 7 out and put it into the index, and we're left with the 7th root of x cubed. There's nothing we can do with that, so we leave it there. Up next, we've got 0 and negative exponents. So a 0 exponent, here's the rule. Anything raised to the 0th power is going to be 1. The only exception is if the base is 0. So 0 to the 0th power is 0, but anything else raised to the 0th power is always going to be 1. Then with negative exponents, so you say you have a to the negative n. What we do with that is we take whatever the base is and we flip it underneath into the denominator. So if we have a to the negative n, anytime you see that negative exponent automatically tells you to flip it either down into the denominator, or if the base starts in the denominator, flip it up into the numerator. So a to the negative n is equal to 1 over a to the n. One very important rule with this, only the base that's attached to the exponent is affected by the negative exponent. So let's say you had a to the negative n times b. Only a to the n would be flipped into the denominator. The b would be completely unaffected. It would stay in the numerator. So you would have b over a to the n. In problem number 2a, you're given what is y to the negative 3.5 in radical form. So what my suggestion always is go ahead and change a decimal over to a fraction. So you're going to end up with y to the negative 7/2. So that negative exponent immediately tells you take that base and flip it down into the denominator. So you'd end up with 1 over y to the 7 halves. At this point, you're going to take the denominator of the exponent and move it into the index. And you would end up with 1 over the square root of y to the 7th. For right now, we're going to leave it as is. We're not going to rationalize it. But know in the future, you would have to rationalize that radical in order to not have a radical in the denominator. For 2b, we're given what is the square root of a to the 5th in exponential form. So what we're going to do is, we know that since we've got a square root, the index is 2, we're going to take that 2, move it up underneath the 5, and that's going to become a to the 5 halves. Now for problem 2b, we're going to be given a little bit different thing that we haven't seen yet. The 5th root of b, and then that itself is cubed. So one of the rules that you need to know is that if you have an exponent on the outside of the parentheses, then what you can do is you can take that and you can plug it in to the radicand. So instead of saying the 5th root of b then raised to the 3rd, you could do the 5th root of b to the 3rd. And then once you've got that, you can take the 5, move it up underneath the 3, and that's going to give you b to the 3/5. So in problem number 3, we're going to take a look at a word problem. Use the function p equals d to the 3 halves, where d is the distance to the sun in astronomical units, which is also the distance from the Earth to the sun, and then how many Earth years does it take Mars to orbit the sun? So we start off with our formula, p equals d to the 3 halves. We know that from the sun to Mars is 1.52 AU. So we're going to put 1.52 in for d, and then we would use a calculator for this. 1.52 raised to the 3 halves is going to be approximately 1.87 years. So it takes 1.87 years for Mars to orbit the sun. For problem number 4, we're given what is the 4th root of x cubed over the 8th root of x squared in simplest form. So we start off with our original problem, and if you look at this, we know that anytime that you want to divide or multiply radicals, you have to have the same index. Well, until now. Now that we know how to use rational exponents, we can actually use rational exponents to solve these problems. So take that 4th root, and you're going to move it up underneath the 3. So you get x to the 3/4. Take the 8th root and move it up under the 2, and you get x to the 2/8. Now simplify. So x to the 3/4 over x to the 1/4. We don't want to leave it as 2/8 because we can just go ahead and simplify that down to a simpler fraction. Now, one of the rules that you should remember from earlier on is that anytime that you're dividing bases, you're going to subtract exponents. So since we're dividing x's, we're going to subtract those exponents. So we get x to the 3/4 minus 1/4, which is x to the 2/4, which simplified is x to the 1/2. And then you take that 2, move it into the nook of the index, and you get the square root of x. For problem number 5a, what is 16 to the negative 2.5? So again, take that negative 2.5 and change it into a fraction. So negative 2.5 expressed as a fraction is negative 5 over 2. That negative exponent tells you that we're going to flip the base down into a denominator. So we get 1 over 16 to the 5 halves. Now, one of the things that we can do here is we can simplify this base. So we have a 16, but we can take that all the way down to 2. So 16 written in its lowest base is 2 to the 4th. So now we've got 1 over 2 to the 4th to the 5 halves. Remember that anytime you raise an exponent by another exponent, you're going to multiply those exponents. So we can go 4 times 5 is 20, divided by 2 is 10. Or we could take the 4 and the 2 and we could reduce those. And the 2 goes away, the 4 becomes a 2. 2 times 5 is 10. So either way you want to do it, we end up with 1 over 2 to the 10th. 2 to the 10th is 1024. So the solution is 1 over 1024. For problem number 5b, you're given negative 32 to the 4/5. So take that base and simplify it as much as possible, which is going to give you negative 2 to the 5th, and then that's going to be raised to the 4/5. So again, remember your rule. Anytime that you raise an exponent by an exponent, you're going to multiply them. The 2 5s cancel out. You're just left with a 4. So negative 2 to the 4th is 16. For problem number 6a, we're asked negative 8x, square root of xy, and everything in there raised to the 2/3. So one of the things that you definitely have to know is that 2/3 exponent applies to everything that's inside of those parentheses. So it applies to the negative 8, it applies to the x, it applies to the square root of x, and it applies to the square root of y. So let's go ahead and simplify everything first and make everything into a rational exponent if necessary. So that gives us negative 2 cubed, then x, then the square root of x becomes x to the 1/2, and the square root of y becomes y to the 1/2. And again, all of that is still being raised to the 2/3. Then let's take the x to the first and the x to the 1/2 and combine those together. So x to the first is the same thing as saying x to the 2 over 2. So if we add 2 over 2 and 1 over 2, we get 3 over 2. So now we've got negative 2 cubed, x to the 3/2, y to the 1/2, and then everything raised to the 2/3. So now go ahead and distribute that 2/3 through to every single exponent that we have. So negative 2 cubed becomes negative 2 squared. X to the 3/2 raised to the 2/3, all of that cancels out, so you're just left with x. Then y to the 1/2 raised to the 2/3, you cancel out the 2's and you're left with 1/3, so y to the 1/3. So now remembering that we can't leave anything as a rational exponent, we're going to go ahead and simplify that negative 2 squared. That gives us 4. The x stays the same. And then the y becomes the cubed root of y. Finally, we've got 16y to the negative 8th raised to the negative 3/4. So again, let's go ahead and convert everything to its lowest possible base, which is going to be 2 to the 4th, y to the negative 8th, and then raised to the negative 3/4. Then distribute the negative 3/4 through to both of those, to both the 2 and to the y. So when we do that, we end up with 2 to the negative 3rd, y to the 6th. So the original positive exponent becomes negative, and the original negative exponent now becomes positive. So 2 to the negative 3rd is going to get flipped down into the denominator. So that leaves us with y to the 6th over 2 to the 3rd. 2 to the 3rd simplifies to 8, so the answer is y to the 6th over 8.